This one you have to figure it on your own. It is in the textbook, and notice I have a little caveat up here. Continue to look at induction. The force field part is not testable. This is what you get to in grade 12 physics. You start looking at force fields. Many of you have probably seen a magnetic force field with iron filings, and I think everybody, you just have to watch one Avengers movie, and there's some giant gravity well in outer space. And you can use this idea of the force field to figure out which way objects are going to move. Electric fields are very similar to magnetic and gravitational fields, but gravity always sucks. Magnetism and electricity can blow as well. So they both suck and blow at the same time. These two are attracted to each other, and the field lines would look like this, drawing together. These two are repelled from each other, and the field lines would look like this. You get into field theory and senior physics and on. This fielding is very hard to shield in many cases. To polarize a material is to make it have poles, like north or south, positive or negative. A neutral object could be minding its own business when a positive comes by. The electrons swarm to the front to be near the positives, while the positives run away to the rear to avoid the other positive. This object has now been polarized, or what we'd say charged inductively. So if this positive wanders away, a neutral situation would appear. Now, why didn't the electrons jump to reach the positive? Because the air may provide sufficient insulation to prevent that. What this means is anytime a charge approaches a neutral object, the neutral object will present to the charge the thing it wants the most. So if a negative approached this object, the positive would come forward, and they would be trapped here. So this positive is quite likely to sit there for eternity looking at the electrons it desires. Does that remind you of something in Harry Potter? Anything you approach something and it shows you the most lovely thing in the world, the thing you desire the most, and you can get trapped there. So the neutral object is like the mirror of Erised to any charge that approaches it. Now, what if the object is not tied down? If the object is not tied down and the charges can't jump, the whole object may move. So these electrons may wind up physically dragging this, let's say it's a water drop, they may physically drag it forward. Again, the positives are like, no, 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 but they're further away. So they can't, the droplet might stretch a little bit, but these guys may drag it forward. So this little puppy, if he's after something and this guy's not strong enough, the puppy's desire to reach the opposite charge equivalent this is what would happen. So this is why dust always heads towards a charged object. Now, if the leash breaks, that would be the spark, and this guy would stop moving. Okay, so once the sparks jump, anything on the Van de Graaff that's showing induction just stops. So here's how we can induce a permanent charge on an object. We take an object that's neutral and bring a charge near it. The negatives collect here, but if we attach a ground wire, the protons, or the positive charges, I shouldn't say protons, they back away. And at that point, if we cut the ground wire, these charges cannot come back. We can remove the positive now, and we are left with an object that is net negative. So we can trap the opposite state by induction by doing that. And now you have a permanently charged object without actually touching it to the other one. One application of induced charge is electrostatic spray painting. I suggest you read 470 and figure it out yourself. It's not hard to do, but you can do this. And it is definitely testable. We will be having a quiz on static, and it will be on the final exam. A natural phenomenon of this occurs when we get charge separation in a cloud. A giant thundercloud is like the Van de Graaff machine. It may charge separate, making the bottom of the cloud negative and the top positive. This means the Van de Graaff throws the spark this way, from the negative to the positive. So internal to the cloud, when the whole cloud lights up in what we call sheet lightning, there's an upwards bolt periodically neutralizing the cloud. Here's where your house gets into the situation. Before a thundercloud appears, your house is quite neutral. When the thunderstorm appears over your house and the bottom is strongly negative, we get this induced charge separation. Positive swarming the top of your house to get near those electrons, and electrons in the ground backing away as far as they could. So all of a sudden, your house does become charged by induction. And now the electrons have two choices: jump to the cloud and ground out inside the cloud, or they could fire a bolt down to your house to get rid of the spare electrons. So you don't need to charge your house. It's charging by this force field effect. And if you were outdoors, you would start to feel your hair stand on end. But the opposite situation can also exist. If the bottom of the cloud is positive, then electrons will swarm into your house to try to reach them, and the positives will move away. And in this case, the lightning bolt goes up, so your house can hit the clouds with lightning. Now, which one is more likely to burn down your house? The lightning bolt that starts from a single spot on your house and goes up to the clouds, or the lightning bolt that fans out from the clouds? But either way, your house cannot pretend to be Switzerland. When the war is coming, it's going to take the opposite side of whatever's approaching it. It can't be helped. Then what's the point of the lightning rod? Most people misunderstand the lightning rod. They think its job is to take the lightning around the house. And yes, it will do that. If a negative bolt from a cloud hits the lightning rod, it will pipe the electrons around your house to ground and avoid burning down your house. And here's the ground wire for a lightning rod right there going into the earth. You shouldn't hang around this ground plane, because if a lightning bolt was successfully piped into the ground and you were right here in the dirt around it, you could get spray, and it would go in one leg, across, down the other leg. Chestnuts roasting on the open fire. What about the reverse situation? What most people don't realize is the lightning rod can actually stop the bolt in the first place. The easiest way to explain this is to assume the ground is negative. This is a better conductive path, so the electrons will flow around your house, go up the lightning rod, and fire a bolt to the cloud. But this is an excellent conductor. So the electrons get running really fast up this, and they may spray off the tip of the lightning rod and show a faint blue glow, and you'll hear like a frying bacon sound or a sss. And what's happening is the electrons are leaking off the sharp, pointy lightning rod, and they can leak the machine or leak the charge so swiftly that a lightning bolt never happens. So a lightning rod can actually prevent the lightning strike in the first place. And this diagram is testable. Now, how do you convince a person when they put a lightning rod on their house? You go like, I paid for one of them dang lightning rods and my house ain't been hit by lightning in 30 years. Because the lightning rod's doing its job. How do you make it clear to a person that it's doing their job? If you live on a farm and there's lightning rods in your old barn, on a stormy night, you may see a faint blue glow, but it's really dim. So many lightning rods employed this orb here. It's decorative, but this orb will flash as it's discharging electrons that are too dim to see. So you could say to the person, look, every time you go outside and you see a flicker of light from that orb, that was a lightning bolt prevented that could have destroyed